Good morning, ladies and gentlemen, and welcome to the most important chapter in the life of Rosetta. In 1.5 hours, Rosetta will arrive at comet Churyumov Gerasimenko. And after 10 years in space and thousands of millions of kilometers traveled, and you see here the launch, we will stop to ask, are we there yet? We all will be there. And we will see live, either at home at our screens or here at the European Space Operations Center in Darmstadt, the arrival of Rosetta. And this, of course, will be the decisive moment, but we have other program highlights lined up for you as well. There is the science. We will present the latest science of Rosetta. We will show you the latest images taken just a few days ago. There will be a rival movie where you can see how the nucleus was growing bigger and bigger in the navigation camera. And as we speak, we take another image. It will be downloaded now. Hopefully we can process it in time and we will show it to you in the afternoon. That means that's what Rosetta will see now when it's going to arrive. We have been inviting lots of experts and scientists to talk to you, and please talk to my colleagues of the media relations team. They will be happy to help you to make the connection. But now, before we start into the program, I would like to invite Thomas Reiter, the Director of Human Spaceflight and Operations, for a welcome. Ladies and gentlemen, thank you.
Thank you very much. Good morning, ladies and gentlemen. It's a real great pleasure for me to welcome you today here at the European Space Operations Center, ESOC in Darmstadt. It's about half a year ago that we gathered in this place to witness the so-called awakening of Rosetta. After more than 2.5 years of hibernation, Rosetta, our European comet chaser. Traveling about 10 years through our solar system, Rosetta got ready to prepare for the rendezvous with the comet Churyumov-Gerasimenko. And today, Rosetta has reached its destination. Now, before you will hear some more details about this exciting mission, please allow me to welcome some of our representatives of the federal and state government, local administration, and ESA member states. Representing the federal government of Germany, I welcome Undersecretary of State Ms. Zypries. Representing the government of the state of Hessen, welcome to the Undersecretary of State, Mr. Ingmar Jung. From the federal parliament, I welcome Mr. Wilsch. From the Hessen parliament, I welcome Ms. Karin Wolf. And from the town of Darmstadt, I welcome our Lord Mayor, Mr. Parch. Furthermore, we have with us today the heads of agencies from 5 of our member states. From the Austrian Agency of Aerospace, I welcome Dr. Harald Posch, who is also the chairman of the ESA Council. From the French Space Agency CNES, I welcome Jean-Yves Le Gall. From the Italian Space Agency ASI, I welcome Professor Roberto Battiston. From the Space Agency of the United Kingdom, a welcome to Dr. David Parker. And from the German Space Agency DLR, I welcome Professor Johann Dietrich Wörner. Also, a cordial welcome to all representatives from the scientific community, the representatives from European space industry. There are 50 companies across 14 European states who are involved in this program, and representing all them, I welcome prime contractor of Airbus Defence and Space, who is represented by Mr. Eckhard Zettelmeier. Also, a welcome to all colleagues from media who share the excitement for spaceflight with us, and of course my colleagues from ESA, our Director General, Jean-Jacques Dordain, our Director for Earth Observation Program, Volker Liebig, and Professor Alvaro Giménez, the ESA Director for Science and Robotic Exploration. Alvaro Giménez will give you some more details on this exciting and challenging part of the Rosetta mission. Now, overall, the journey of Rosetta took actually longer than 10 years of traveling through space, as you can imagine. First thoughts about sending a probe to a comet goes back to as far as the middle of the 80s in the last century. The development of Rosetta started roughly 10 years later in the 90s, leading to a launch of the spacecraft on the 2nd of March 2004 on top of an Ariane 5 rocket from ESA's launch site in Kourou in French Guiana. And from this site we also launched, by the way, last week, the fifth and last ATV, Advanced Transport Vehicle, automated transport vehicle to the International Space Station, which is now on its way to International Space Station and will dock actually on the 12th next week. Coming back to Rosetta, now considering these time scales, first thoughts started in the 80s, development in the 90s of the last decade, it becomes readily apparent that the colleagues sitting at the consoles today and who are in charge of operating the missions are certainly not the same who were involved in the early parts of the mission, namely its development. This is quite typical for space missions, and here a crucial question arises: how to transfer this knowledge from one generation of space engineers to the next. Now, ESA has proven in the past that it was standing up to this challenge. More than 60 ESA satellites successfully operated here in ESOC bear convincing witness of this fact. The successes we celebrate today follow a long tradition, and this is really the key point, depend on daring decisions which have been taken in the past, and often more than 1 or 2 decades ago. Likewise, the successes of tomorrow depend on the decisions we are taking today. Stay tuned in the coming months when we will hear more and more exciting findings from Rosetta. With these thoughts, I would like to hand over now to our Director General, Jean-Jacques Dordain. Thank you very much.
Thomas Reiter, the Director of Human Spaceflight and Operations, and allow me a short introductory moderation. Thomas was already in training when Rosetta was launched, 2nd of March 2004. He kept on training when the first flyby took place on Earth. There were some concerns it might fail, but of course it didn't. Rosetta just passed 2,000 kilometers above our heads about Earth, and we got brilliant images from Earth, and that was already a hint what Rosetta would be able to do later on. But what I wanted to say is Jean-Jacques Dordain was already Director General of the European Space Agency in 2004, so he saw the launch, the 3 flybys in 2005, 2007, 2009 at Earth. Therefore, welcome Jean-Jacques Dordain. Please.
Thank you very much, and welcome to ESOC, which is one of the most important centers of ESA, and for another important event. I must say I am always at ESOC for important events, but today it's an important milestone of the Rosetta mission. This is a rendezvous with a comet, with the last boost of a series of 10, which has taken place since the 20th of January. Because we were here, at least some of us, and especially Thomas and myself, and there are pictures of our smiles, more than smiles, I must say, when we got the signal of Rosetta. And this is before the next important event, which will be the landing of Philae on the comet 67P. I am less gifted than Thomas to name Ukrainian names, so I keep 67P, which is much easier. But we shall land on that comet on the 11th of November. So it makes 2014 the year of Rosetta. This is very clear. So as Thomas said, Rosetta was designed more than 20 years ago and launched 10 years ago on the 2nd of March 2004. I must say that it was a difficult decision to launch Rosetta, because it was after a failure of Ariane 5, and I remember with Jean-Yves Le Gall, who was at Arianespace at that time, that it took some time to decide to launch Rosetta, but we made it, and it was a beautiful launch. But 20 years later, Rosetta is still a unique mission and will stay for very long, a unique mission. Unique by its scientific goal, understanding our origins, which is certainly the best way to understand our future. So we shall look, the scientists will look at our origins. And for that, there are 11 scientific instruments on board the orbiter and 10 scientific instruments on board the lander, which is a lot of data which will be collected. It's unique also by its technology challenges, because to make scientific progress, you cannot make scientific progress without technology progress and without taking the risk of innovation. And we have taken a lot of risk by designing Rosetta. First of all, by the duration of its travel, 10 years, 4 gravitation kicks, 3 gravitation kicks using planet Earth and 1 kick using Mars, to give the speed of 55,000 kilometers per hour, meaning that we are using the planets also as propulsion system, which is an interesting way to use the planets. But also by the harshness of its travel. We went beyond Jupiter, where it was very cold, and in spite of the large solar panels, as you can see, we have tried to give some power to Rosetta, but it was so cold beyond Jupiter that we have decided to put Rosetta in hibernation for 31 months, meaning that for 31 months we had no news from Rosetta. But she woke up on the 20th of January, with some delays, unfortunately, but which has reinforced our pleasure, I must say. But also unique by the accuracy of its navigation. Today, the boost will take place at 400 millions of kilometers, somewhere between Jupiter and Mars, with a spacecraft which is running at 55,000 kilometers per hour, demonstrating once more that the ESOC, this is the best drivers of the world. I have said that many times, but the best drivers of the world are here at ESOC. And and as Thomas was saying, the persons changed at ESA, and even the Director General will change soon. But the person changed because the missions are long enough to have persons changing, but the people of ESA stays the same. They are still the best experts, and that this is thanks to the transmission from one generation to the next one. And I am glad to see Manfred here with us today. I must say that Manfred is not anymore operational, but he is still very active. And I would like to thank you, Manfred, to be with us also today. So Rosetta is another demonstration of the uniqueness of the scientific program of ESA. Because the science program of ESA is the oldest program of ESA. It's 50 years. We are celebrating today 50 years of ESA, this year 50 years of ESA, and it's 50 years that the science program exists. And the science program is 50 years of innovation and 50 years of cooperation. It's cooperation among all member states. This is one of the very few programs where all member states are together. It's today 20 member states working together. But it's not only cooperation among all ESA member states, but it's also cooperation between ESA and the national agencies. Most of the instruments are coming from the national agencies. And the lander filet is also a product coming from the national agencies. And I am glad that all the heads of national agencies, which are today, they are not only the shareholders of ESA, but they are also the partners of ESA. And that it's a demonstration of what means cooperation at ESA. But it's also 50 years of innovation, which has put ESA at the forefront of the progress of knowledge. Because today we are celebrating Rosetta, but we had Huygens in the same room when we landed on Titan. We had the first image of the fossil light coming from Planck. Today it's Rosetta, and I would not like to forget Giotto, which was our first encounter with a comet. So all the history of ESA is made of scientific discoveries and unique discoveries that nobody has done before ESA. So ESA is everywhere in the solar system. We are orbiting around Mars, around Venus. We have landed on the moon. Maybe it was a little bit harsh. We have landed on Titan, that this is for sure. We shall go to Mercury, and meaning that we are everywhere on the solar system, and this is the best way to better understand planet Earth, because what is at stake is the future of planet Earth. So today is just a milestone in the Rosetta mission, an important milestone, obviously. But there is much more to come, not only the landing of Philae, but even much more. The science will come. We shall start to collect scientific data, and this scientific data will be provided to the scientific communities, meaning that they are the ones to make the understanding. We are just providing data. The scientists will make the work, and I am sure that the scientific data that we shall collect will give them for decades of work. So I wish bon courage to all the scientists which are today waiting for the data. So I would like to say, yes, as Thomas was saying, the summer at ESA will be very hot. Last week we have launched the ATV Georges Lemaître. Next week, Georges Lemaître will dock to the International Space Station. 1 week later, we shall launch 2 satellites of Galileo. So meaning that August will be an interesting month for us, without speaking of some activities to prepare the next council at ministerial level. But today, let's concentrate on the event of Rosetta. Enjoy it, because this is your only chance to have a rendezvous with a comet. Thank you very much.
Thank you very much. Ladies and gentlemen, Jean-Jacques Dordain, the Director General of the European Space Agency. And Jean-Jacques already mentioned it. We had 4 flybys. The 4th one was at Mars, and it was called the Euro-Billion Gamble. So why was that? Well, because the spacecraft went behind Mars, and there's no radio communication, so it's just out of control to a certain extent, and that was in the most critical moment, 250 kilometers above the surface of the red planet. But after 15 minutes, Rosetta came around Mars, perfect shape, got exactly the momentum it needed for the other thousands of millions of kilometers. And it also brought, again, nice images back from Mars, and we understood that the cameras are really doing a brilliant job. Ladies and gentlemen, our next guest was at that time the Minister of Justice in Germany. Today she's coordinating the German aerospace policy. Please welcome with me Parliamentary State Secretary at the Federal Ministry of Economic Affairs and Energy, Brigitte Zypries.
Thank you very much, and thank you very much for the opportunity to be part at this arrival at the comet or the rendezvous with the planet. I'm very pleased to be here, and since we've heard by Mr. Reiter and Jean-Jacques Dordain everything about the mission, I think it's my part as a politician to say thank you. Thank you to ESA, and thank you to all the scientists working at ESA and having in the 80s this brilliant idea of how can we go to the space and figure out all that what we are going to see now. So thank you for the former ones, and thank you for the ones today taking care of Rosetta. And I would like to say thank you as well to the people doing your Öffentlichkeitsarbeit. Because I think what you do with the social network, this Wake Up Rosetta and these things for today is a really good thing to interest young people in space and interest young people for working with mathematics and technologies, and that's what we need to continue. So thank you for that. Jetzt könnt ihr mal klatschen. Second, I would like to explain that the 300 million Germany spent in this event is really good spent money. You mentioned, Jean-Jacques Dada, that there are 20 countries working together on ESA and everyone paid his part. Germany paid 300 million, and as I explained today to the press as well, it's very good put money because we need the people looking for new ideas and see what we can get from the space and to get it down to Earth and learn for our life on Earth from space. So I think that's a very good idea, and I hope that there are scientists today which get the ideas of what we can launch in 10 years. So, okay, I know that this is just one event today, and we are going to meet again in November. And I keep my fingers crossed that it's going to work out today and especially in November, because after I saw the first pictures of the comet, I thought it looks like a misbuilt potato, but not like a comet where it's easy to land. So it's going to be a very hard job for you, I suppose, and I wish you all good luck.
So, Madam Minister, just to make sure that you will remember Rosetta.
I will always remember Rosetta.
I would like to offer you a model of the Rosetta orbiter, and I hope
Perfect.
that you will remember that very important day for ESA. And I would like to thank, and especially Germany, because among the member states, I like all my member states equally. But on the science program, Germany is the biggest contributor. So thank you very much for your support.
Thank you. Thank you very much. And this is the... Perfect.
Thank you very much, ladies and gentlemen. Brigitte Zypris, the space coordinator in Germany. Now, we learned already that the trajectory of Rosetta was really a difficult and complex one. We had 3 flybys at Earth and we had 1 at Mars. And even more, those trajectories were calculated in the way that we could visit 2 asteroids. And the first one we visited in 2008 was called Steins. And Rosetta flew by at a distance of around 800 kilometers and took stunning images of this diamond-shaped asteroid. And by the way, Rosetta became the first spacecraft to come close to an E-type asteroid. That's one that has more silicate than iron. It's a difference towards all the others. And this happened in September 2008, and Jan Dietrich Werner was already the chairman of the board of the German Aerospace Center, DLR. And as we heard, DLR is heavily involved in Rosetta, and therefore I would like you to give him a warm welcome, Jan Dietrich Werner from DLR.
Ladies and gentlemen, it's for me also a very special pleasure and honor to be here and to talk a little bit about Rosetta. Rosetta is, of course, a very important milestone for the European space activities. And if we look to space and what we are doing at DLR, we are always looking to what are the grand challenges for today and for tomorrow. You might have your special priority of all these challenges, and there is one very special challenge on the very last line, and this is curiosity. Curiosity is the most important challenge to be communicated, because if children are curious, we are happy, we are proud. If they get older, we call them scientists. And this is a very special understanding about curiosity, and I know that especially for politicians, it's not that easy always to convince parliamentarians to spend a lot of money for all of these activities. So, because all of us are discussing about the Rosetta mission, I would like to look a little bit back in history, even further than only the 10 or 20 years, the launch and the development, to Rosetta. What was Rosetta really? Rosetta was a stone, or is a stone, and this stone is a decree in 3 different languages. So it's a dictionary, a very special dictionary, which gave us some information about how to understand hieroglyphs and others. And so therefore Rosetta, the Rosetta mission, driven by ESA, is a very special mission to understand different things. And at the same time we are discussing about Philae. Philae is a lander, and this name comes from the island of Time, and there is an obelisk which helped us to understand, not us, but our predecessors, to understand also what is on the Rosetta stone. So there is a strong link between Philae and Rosetta, not only for our mission. Now I would like to make a short travel in time with you. And the challenge is that you should think about the time from the Big Bang to today in just 1 year. So consider these 13.7 billion of years is condensed to 1 year. So on the 1st of January there is a Big Bang. And the time scale is that about 100 years is about 0.23 seconds. So for the politicians, I give you an information what that means in your understanding. It's about 0.009 seconds for a legislative period. So not that long with regard to the time from the Big Bang to today. Now if we look into the time scale in the agenda, there is the formation of Sun and Earth on the 9th of September. Afterwards, several activities happened. I will not go into all the details, but on 5.1 seconds before midnight of that year, starting with Big Bang at the very first day and the 31st of December, midnight today, there is just 5.1 second before midnight the stone of Rosetta was produced. So it's before Jesus Christ. And it's before the birthday of ESA. Birthday of ESA is 0.11 seconds before midnight. Then we have 0.02 seconds before midnight, launch of Rosetta with an Ariane 5, I have to say that. It was a very important mission. Now we are at the 31st December, 24 hours today. And there is another important aspect which comes 0.001 second later. This is the landing of Philae kissing of Philae with a comet, whatever you call it. Churyumov, Gerasimenko is so small. To have a landing is a difficult work, maybe a rendezvous and kissing. Okay, so we heard already that this is an ESA mission. And as Jean-Jacques pointed out, it's an ESA mission of all the different member states, which is really what ESA is, all the different member states. And Jean-Jacques also pointed out that the other member states are participating and the agencies are here, and they are not only participating, they are very, very proud about it. For instance, Germany, that we can lead the international consortium for Philae, but also I looked into the internet and it's very easy. If you look to CNES, Rosetta is there. If you look to ASI, Rosetta is there. If you look to NASA, which is not European, not yet, NASA, it's also there. It's also proud about Rosetta, so all the different member states, the agencies are proud, and there are much more than just the agencies, scientists from different institutions, but also, of course, DLR is proud to be part of it, especially because of Philae. So you see there is this understanding that ESA is not just an agency doing some work for the different member states, but ESA is an agency working with the member states, and the member states are working with ESA. Now, I showed you that the history is a long time, and that Rosetta is giving us some information about the history, maybe also the future of our universe, or at least our solar system. As I mentioned, this is a little bit out of the time scale of politicians, a little bit. But I can give you also something, and Madame Cyprus also said it, that we should see what comes down to earth from all these scientific endeavors. And there's one very concrete result we have already from Rosetta, and this is transfer to an earthly application. One of the sensors on board is now used as an early fire detection system, and not only one, but 160 are installed in Brandenburg, close to Berlin, to discover very early, any type of forest fire. So you see, we have everything. We have the long-term aspect of Rosetta. We have also a short-term. We have the international and European aspect of Rosetta. So Rosetta is for sure one of the key milestones of ESA and space in Europe. Thank you very much.
Thank you very much, Jan-Dietrich Wörner from DLR. Ladies and gentlemen, there was a second asteroid on the way called Lutetia, and that was really an extraordinary flyby. We came as close as 3 kilometers and at a speed of 45,000 kilometers per hour, and even more at a distance of 450 million kilometers far away from Earth. All operated from here. And the reward, stunning images of this 100-kilometer wide asteroid and a lot of scientific data. Clearly, Rosetta has already, during its journey, promised a lot, and today I can promise we will see even more. As you know, Rosetta is an ESA mission with contributions of all ESA member states and NASA, and one of the main European contributors is the French space agency CNES. Please welcome with me Jean-Yves Le Gall, the president of CNES.
So thank you, dear State Secretary Brigitte Zipris, dear Jean-Jacques Dordain, dear Jan Werner, dear Roberto Battiston, dear David Parker. I probably forget some other friends, but so dear friends. Today, in fact, is the end of the beginning and the beginning of the science mission. And as we saw it, we had a perfect launch by Ariane 5 in 2004, and as Jean-Jacques said, I was at this time in Arianespace, and it was probably, I can say, the most important launch in my life, because it was a very tough period. We had a problem on Ariane 5 in 2002, and we were supposed to launch Rosetta in early 2003. I think that the launch date was planned to be on the 6th of January 2003. And we had to decide between Christmas and New Year's Day to postpone the launch and to go to the comet Churyumov-Gerasimenko instead of the comet Versfallen. And if Rosetta had been finally launched to Versfallen, the encounter would have taken place in 2010, and because of this postponement, we are now in 2014. And in fact, for me, I should confess that I like comets. I love comets. And my first rendezvous was with the comet Halley. And I can remember because we launched it with Ariane a long time ago. It was the 2nd of July 1995. For me, it was my first Ariane launch. And the encounter with the comet Halley appeared in fact on the 13th of March 1986. And in France, we organized what was so-called the Night of a Comet, and it was a very special period because, as Jean-Jacques said, we have some changes, and at this time in France, there was a big change in the government. The governments also are changing, but we had a very special night. It was in Cité de la Science, which is today chaired by Claudie Agnoret, another friend of space. And it was a really, really impressive night. But unfortunately, as you know, Giotto had a very quick encounter with the nucleus of the comet Halley. It took a few seconds. And already at this time, we started to speak about Rosetta. And I dreamed about the day when we will have a much longer encounter. And today, the dream is going to be alive because of this rendezvous with this comet. And so this rendezvous will occur after a cruising of 10 years. And this arrival phase, in fact, is the most complex and exotic trajectory we have ever seen. And I want to thank myself also the outstanding work of the ESOC team. Because of you, Rosetta completed a very surprising spiral formed of triangles to arrive slowly and safely at the already active and until now unknown object. And I should say that now that I am in CNES, we are very proud to be involved in this 20-year project. We have contributed to several instruments, among them the radar developed in Grenoble. I quote Grenoble because, as you probably know, this is the hometown of my minister, Mrs. Fioraso, and I am sure that she's looking at us, so I think that is a good point to speak about Grenoble. Thank you, Mrs. Minister. But we have also the Landers cameras, which are built in Orsay, and they will image the landscape of a comet from its surface for the first time. But we were also closely involved in the development of the Philae lander. Together we have our friends from DLR, as Jan told us. And this lander, in fact, will have the incredible task of landing on the nucleus next November. I think that it will be on the 11th of November, and this year, 11th of November, will be known because of the landing of Philae, which is an excellent thing. We have also developed in Toulouse the Science Operation and Navigation Center, the SONC, to coordinate the 10 scientific instruments in line with scientific requirements and the lander resources. And we have also devised the automatic sequence that the lander and its instruments will perform during the descent and after landing on the comet, and we are in charge of mission analysis of Philae. So you see that a lot of work will be made in Rosetta everywhere in Europe, and in particular in France. And in France we have a 20-strong team at CNES, and during the last decades, the last 2 decades, we invested in Rosetta more than 215 million euros, and I can tell you that I consider that it is probably one of the best investments made by France and CNES in the field of space, because we are going to have, in fact, an extraordinary achievement with the landing of Philae and the encounter of Rosetta with the comet. And in total, we have more than 80 scientists who are involved in the mission from 17 laboratories. So I would like to congratulate all the teams of scientists and engineers for the work which has been accomplished up to now, and I wish a very, very great success for the mission, for Rosetta, for the landing of Philae, with a wealth of fine and very exciting scientific results. Once again, thank you and bravo.
Much, ladies and gentlemen, Jean-Yves Legal from CNES. Now, the comet comes into the inner solar system and we can visit it, but first we need to go out very, very far, and that means into the orbit of Jupiter, 800 million kilometers far out. And there, well, there's simply not enough sunlight to operate the spacecraft with the power needed, so even these huge 30-meter solar panels made out of gallium arsenide are not doing the job. What you do? Well, you switch the spacecraft off. And that's nothing a mission manager really wants to do. In fact, probably it's the nightmare of a mission manager to have a spacecraft in space, in orbit, and you have to switch it off. Well, after 31 months, it woke up again, and I can tell you the relief was really, really great in this room, and of course also at the Italian Space Agency. Please welcome with me Roberto Battiston from ASI.
Their Undersecretary for Research and Science, Mrs. Zypris, their friends Jean-Jacques, Jean-Yves, Jan, David, and most warmly their member of the ESOC team and of the scientists which made Rosetta possible. I would like to stress this particular thanks because I'm a scientist and I spent also 20 years on a mission, so I understand you today how much you must be proud of what you accomplished. So Rosetta is a mission of records. Getting there in top of the 10 years of travel and 20 years of preparation is like throwing a small grain of salt from Darmstadt to hit a given atom in Rome. It's impossible, and you made it. Italy has participated to this mission, and we are proud of having done so, as has been recalled before, because the investment done for this kind of science is really well done, provided we can get to these outstanding success and results. Italy, over this period of time, has invested about 100 million euro, counting the investment on the industrial side and the support for the scientists. But most important, it has contributed to a number of instruments which are essential for the operation, the approach, the measurement of the comet properties, the temperature, the dust around it, and to make eventually, after the landing, a drill inside the surface of the comet to understand what is behind the crust, the tiny crust of this comet. So I would like to thank today the colleague of the Institute of Astrophysics, Italian Institute of Astrophysics, INAF, from Rome, from Naples, the University of Milano, of Padua, which are the key player in the designing, running, contributing to the various instruments, which are called VIRTIS, SD2, JADA, WOC. These names may not mean so much to most of you, but they mean very much to the few of you which made this mission a reality. And on top of that, I have to thank Thales Alenia Space, which also contributed on the industrial side in a way which is so important. But as I was mentioned before, 20 years is a long time, and what we are collecting today is a testimony of ideas, decision, and acts, scientific decisions which were made long ago. And I think it's very important today to recall one of the figures which made Rosetta a reality, Angioetta Corradini, which is not with us today, but is an example of how the testimony for science, for research, has been transferred to the people who are here today. I would like to recall her unstoppable activity, unshaking enthusiasm, and unrivaled intelligence. I think planetary science is really in debt to Angioetta very much, and I would like to applaud her. We are today facing an example of what is called big science, global science. You know, I'm coming from large science in particle physics, and so I'm kind of used to that. But you know, in fundamental research, there is always the idea maybe you can get some revolutionary result by making a very clever small experiment which can shortcut the difficulty on finding the law of nature. But with space exploration and planetary science, you cannot do that. There is no free lunch. You really have to go there. And this is why we need a large organization like ESA. We can do that only working together, only putting together the competence, the resources, but the people, the professional, the idea and the enthusiasm which can keep together teams of this quality for long enough to reach these goals. Rosetta is also an history of strength and capability to resist against difficulties. Not only natural difficulties, not only traveling far away and getting a small dot in the midst of nowhere. This is normal business for scientists and technologies, but most important to face against the unknown. I mean, the idea of landing on a comet was contemplated long ago, well before the birth of Rosetta, but failed because NASA eventually pulled out for such an enterprise for various reasons. So ESA had to proceed basically alone. And this is a demonstration how much this decision has been fruitful and most important has been showing the strength of Europe and the strength of the states working together. Another difficulty which has been really professionally faced and solved has been the change of comet. Yeah, there zillion of comets out there, but changing from one to the other is not something you can do it easily, and the team made it possible really in a short time with perfect result. So 20 years have gone, and let us, the fun begin. Thank you so much.
Thank you very much, Roberto Battiston from ASI. And now, ladies and gentlemen, we are approaching the moment of truth. Soon we will know whether the last maneuver of Rosetta will be successful or not. And of course it will. I have no doubt about this, but it's time for me to say goodbye and to hand over into the main control room to my co-moderator Monica Jones, who will report from there as things happen. And you can stay here and wait a little bit till we have been establishing the lines, and please cross your fingers for the biggest moment in the life of Rosetta, its arrival at comet 67P Churyumov Gerasimenko. Thank you.
Rosetta, are we there yet? Are we there yet? Are we there yet? Are we there yet? Rosetta, are we there yet? Are we there yet? Are we there?
Are we there yet? Well, we're certainly getting there. Rosetta is just about 100 kilometers away from the comet it's been chasing over the past 10 years, and now Rosetta is close enough for the two of them to finally rendezvous. And we're here to witness this event and give you all the facts and figures. So welcome to our special coverage coming live to you from ESOC in Darmstadt, Germany. I'm Monica Jones, and I'm here in the main control room. Now, the last time I was inside this room was back in January, on the 20th of January, the day when Rosetta, after months of hibernation in deep space, woke up. As you can imagine, that day had quite a few tense moments, but in the end, well, see for yourself. Today. Then we talk about challenges also in the past, leaking Well, happy memories, certainly. Also for the gentleman who's standing right next to me, Paolo Ferri. He's ESA's head of operations sections. You've been part of the Rosetta mission right from the start. That was quite an emotional day back then, was it?
Well, the launch was an emotional day. We had many emotional days, and then we came to this wake up 10 years later. After 2.5 years, no signal. This was incredible, and well, you've seen it also from the pictures.
Yeah, but of course, Rosetta is, the story isn't over yet. We have another very exciting day today, a very complex maneuver, which I believe was initiated here, and you're in touch here all the time with Rosetta. How nervous are you today?
Compared to January, this is much better. The signal is there. Our people are in continuous contact with the probe, so we see that everything is going very well. So the tension is lower now. On the other hand, it is a very important moment. It's a milestone. We get there. We have arrived after more than 10 years trip. So emotionally, we are very excited.
And you should be, probably, because after 10 years, you've had to handle 1 or 2 challenges on the way. I remember there were some leaking gas tanks and stuff, but you sorted it all out.
Well, there were many challenges on the way. We had to do many things. Also, we have to learn to play with the spacecraft, as you do with many missions. Yes, there were also some hardware issues that, like the leak in the high pressure side. And yes, over the 10 years, there was time to do tests on ground, to develop new procedures, new trajectories, and up to now we've shown that all the work has paid off, and we are at the target with basically no main concern for the future.
And just briefly, because obviously all the work does not only include one generation of scientists, but this is a long-term mission. There are many generations. How do you ensure the transfer of know-how?
Well, first of all, Rosetta is such a unique and fascinating mission that people that have the temptation to go away, they always come back, like with the rubber band. Yeah? So we live this. We have many people that maybe left the project for a while and came back, maybe in a different position. We were also lucky that around Rosetta we started 2 similar missions, similar from an operation point of view, interplanetary missions, Venus Express, Mars Express, and we could give career opportunities or little breaks to various people that could grow and then come back. So we have not lost that much expertise. Many people of the beginning are back. At the same time, we got new, fresh people, younger ones, motivated.
And one who is very motivated is standing right behind you, Paolo. If I may interrupt you at this point, thank you very much. Good to see you again. Let me bring in Matt Taylor right now, who of course is ESA's Rosetta project scientist. Come a bit closer. Again, just like in January, I've got a short arm here. So you coordinate the science between ESA and the Rosetta scientists. Now, how is science shaping up so far?
Science is shaping up wonderfully and very quickly, but that's to be expected because Rosetta is the sexiest science mission, the sexiest space mission that's ever been. Around 7th of May this year, we started our science operations. At that time, we were about 1.5 million kilometres away from the comet. At that time, only OSIRIS, our scientific eye, could see the comet and started to infer what we're starting to see now, that something special was happening. Subsequently, we've seen MIRO, the sub-millimetre spectrometer that looks at that particular wavelength of light, reveal some outgassing activity. And then more recently, VERTIS is starting to reveal activity or temperature around the nucleus.
And we'll hear a bit more about these instruments. Of course, back in January, you promised that we're going to do groundbreaking science. And you obviously started already, even though Rosetta was miles away. Now we're much closer to the comet. What can we expect?
Yeah, well, MIRO, VERTIS, all of the instruments are still banging on. They're still giving us fantastic science as we creep closer and closer to the comet. And that's important. As we get closer, the range decreases, and then we come into range of some of the other instruments. We've seen evidence of the outgassing of the comet, so that the outer atmosphere of the comet developing. This is made of dust and gas. We have instruments on board that will start sniffing for this gas. So the gas detector will sniff and taste the gas. We'll also be collecting some of this dust, catching this dust and touching the coma itself. Hopefully that will actually occur sometime this week, so everything's just about there. Now as this coma develops and starts to flow away from the nucleus, it'll start to impinge on the outer atmosphere of the sun itself, the solar wind. We have a plasma package on Rosetta that's trying to investigate that interaction. At the moment, they've only really seen pristine solar wind, but there may be some indications, little wiggles there that indicate that the comet's in their signal as well.
And why are these measurements important right now?
they're fundamentally important. They set a baseline for the rest of the mission scientifically, but also in the short term, we have a task to do. We want to characterize the nucleus, the comet, the activity, to try and set up and start the process of deciding where to land in November. That's basically the fundamental thing that we're doing at the moment. In addition, we have an activity group. These guys are cometry experts, instrument specialists. They're also backed up by my colleagues here at ESOC, but also the SGS down in ESAC in Madrid, the Science Ground segment, who are helping us trying to look at how the activity is working at the moment and then project what we think it's going to be doing after the landing in November. That's important to constrain how the scientific operations are going to be done in that time frame, and that's a fun task.
So a lot of busy people, a busy time ahead. What can we look forward to in the months to come?
Well, once we've got the rendezvous done, we're going to ride alongside this comet. We're going to have a ringside seat as we go from this rather inert object now through perihelion. That's the closest approach to the sun next year in summer. And as it starts to move away from the sun, that gives us this ringside seat of this evolution, this dynamic evolution, this fantastic body. It's going to be an awesome ride. Stay tuned.
We certainly will. Matt Taylor, thank you very much and best of luck today. And of course, Rosetta has many instruments on board, also a navigation camera. And Frank Budnik is the flight dynamic expert, and he's here with us because Rosetta's navigation camera has collected quite a few interesting images. It's a bit like Rosetta's eye that allows us and everybody here in the main control room, of course, to get a glimpse at what Rosetta is seeing as it approaches the comet. And I think we've prepared something. You can talk us through a bit.
Yeah, okay. This is what we see is the latest images of the comet as seen from the navigation camera, which starts last Friday when we started hourly images, and from then onward we are at a distance at about 1,000 kilometers, and we see very clearly how we get closer and closer. We did more maneuver in the meantime, and the latest image in the sequence is at a distance of about a bit more than 100 kilometers, which is actually from this morning. So this series of images we take for navigating, for computing the maneuver commands, and start of these images were actually used to compute the maneuver parameters for today's maneuver.
And of course about this maneuver you will tell us much more about later. Frank, thank you very much for now. We'll catch up with you in just a few moments time, but as I can see the clock is ticking and we're just a minute away from this maneuver that is taking place there on board Rosetta. I'm here with the spacecraft operations manager Sylvain Laudiot. An exciting moment. What's the status? Are we ready to go?
So we're go for the maneuver. We don't have contact with the spacecraft right now. The spacecraft is slewing to the altitude of the maneuver, which is expected. The Huygens antenna cannot point to Earth right now, but we'll go for the maneuver, and the last telemetry is about 45 minutes old now, and everything was nominal.
Mm-hmm. So how long will this maneuver take, which is about to start in less than 30 seconds, briefly?
So 6 minutes 26, and it's about to start on board. We have to wait 22 minutes to get the results on ground, of course.
Okay, Sylvain, I'll catch up with you. Let's keep an eye on the clock now. All right. Now, we couldn't see a thing that's going on apart from the clock going. And what's going on?
Well, nominally the maneuver has started on board now. And, okay, we have to see and just wait for the telemetry.
Okay, that's part of your job, of course, Sylvain. Thank you very much. We'll be catching up with you later again, of course, as well. Now, as you know, it's often said that the journey is just as much fun and it's just as exciting as the destination itself. And in Rosetta's case, that is certainly true. So we've got a bit of time. So let's take a moment to look at some of the highlights since Rosetta's launch back in 2004.
10 years ago in Kourou, French Guiana, the Rosetta spacecraft set off on a breathtaking mission to rendezvous with a comet. In order to reach its target, Rosetta played a game of cosmic pool with 2 of the planets in our solar system. It swung by the Earth 3 times and once around Mars for a gravitational push on its long journey. In 2008, Rosetta imaged asteroid Steins, one of the millions of asteroids orbiting the Sun between Mars and Jupiter. Steins revealed itself to be a diamond-shaped rock covered in impact craters. In 2010, Rosetta met up with a different asteroid, Lutetia, believed to be around 4.5 billion years old, a remnant from when the solar system was formed. Covered in grooves, fractures and fault lines, one of its 350 craters stretches for 57 kilometres, the remains of a dramatic collision. Its composition also hints at a metallic core. After entering deep space, the spacecraft put all but essential operations into temporary hibernation in June 2011. Rosetta builds on the legacy of Giotto, ESA's first deep space mission and the first to chase a comet. Giotto made history as part of an international fleet of 5 spacecraft when it approached Halley's Comet in 1985. It got within 600 kilometres, producing a number of spectacular images, including close-ups of the comet's nucleus. Rosetta will go even closer to a comet, orbiting a comet for the first time and landing on its surface.
Well, I've landed now in what is known as the briefing room just outside the main control room in order to talk a bit more with the mission's scientists. And I would like to start with the one right next to me, Holger Sirks, principal investigator of Osiris. It's a 35 kilogram, 4 megapixel camera on board of Rosetta. And Holger, it's good to see you again. You were talking to me back in January when you promised me that this wonderful camera will provide us with fantastic high resolution, astonishing resolution images. Has Osiris delivered?
Yes, it did. So we turned on the instrument on 20th of March and our target comet was still sub-pixel. So it took us up to 16th of June to fill one single pixel of our sensor with the comet. And it took us another month up to 14th of July really to get something like 20 pixel across on our sensor, which is something like 2 hairs filled with pixel of the nucleus. So what I'm showing here is a rotational movie. So this is what we typically take. So 10 degrees of rotation, one image of the nucleus, and work then into a rotational movie here. So you see processed and the unprocessed raw data here. This is really pixel by pixel as coming down from Rosetta. From this we can work a shape model. And so this was taken a few days later and worked into the first shape, and it was just so surprising to see, well, this is not a hull-shaped body, so as we thought from the light curve reduction.
It's got a lot of nicknames already because of that.
Lots of nicknames. It looks bilo. We don't know if it's a contact binary or is it carved like this by activity. And it's so amazing to see this made of a 30 pixel across image sequence, to see this wonderful shape model coming up. So coming closer, it took a long stretch of time to see high-res resolution images. So it took really long. So this was coming down this weekend, and we released it. It was not even made for surface. This is one image taken out of a dust search sequence. It has some stuff on there, so it's a bit overexposed. It has blemishes, but it's really great stuff to see structure coming up on the surface. So real topography, so bright spots, darker spots, and real stuff now in high res. What we thought this weekend. But it's first of all, it's not all about the nucleus. So we also see activity. So we have seen the surprising outburst on 30th of April, so going up and then decaying in 2 weeks of time, and it was gone. So back to baseline. Now, being close, this is an image taken with the wide-angle camera, so on Sunday, so heavily overexposed, so the nucleus overexposed 100 times, such that we can see the faint structures, the jet really worked out in this image. And but then we want to go back to the nucleus. You want to see the nucleus, and here it goes. So this is an image coming down on, taken on 3rd of August, coming down on 4th. This here we are talking 5.5 meters pixel resolution, and it's the best comet nucleus ever resolved in space. So we see lots of structures, so the bilobe structures, the deep bite, so about 1,000 meters deep. We see a big depression here on the head of it. We see the brightness variation across surface, cliffs about 150 meters high, and imagine this is a rubble pile like ashes or so. So it's porous. So how can this work this way by outgassing, by shaping throughout orbit? We also see smooth areas, planes coming up. But it is not only this shot, it also has a backside. Woof. So this is the backside, and we resolve boulders. So these are boulders of house size, 10 meters size and bigger, and they also vary in brightness. We'll have to understand why and what it is really made of. Also very sharp edges, and this is what we got by yesterday, and we are getting
There's
more
more?
images. There's more to come today. It's just streaming down, and we'll work it this afternoon, and hope for the best to show more.
So now we have a really good idea already what 67p really looks like, and you will have even more beauty shots for us later this afternoon. Before I let you go, just briefly, back in January you told me that the comet is important to you because it is a story about us. What does this comet, so far from what you've seen, tell you about us, about you?
Well, it will be the key in cometary science, and it's the beginning of a story of learning about. So where did it form? What does it tell us about the water we are, and the early solar system? So there is a story to come. We are just beginning to build it up, to go with this story.
Well, thank you so much, Holger, for sharing these wonderful images with us. I will now ask two other scientists here while you're setting it up kindly enough for us. Thank you very much, Holger Sirks. And next to me right now is the next scientist already who is eager to tell us about his findings, Fabrizio Capaccioni. He is the PI of VIRTIS, and VIRTIS stands for Visible and Infrared Thermal Imaging Spectrometer. It's divided into two channels, mapping channel and high resolution channel. Just briefly, what do we have to think about that?
Yeah. Okay, yes. As you said, that we have two channels. The mapping channels is like a camera, like Holger's camera, but with a lower resolution, but it has the capability of observing in more than the usual 3 colors of a photographic camera. It covers the full spectrum in 860 colors, covering the spectrum from the ultraviolet to the thermal. And that will be used essentially to study the nucleus and to study the composition of the nucleus and the thermal emissions, so the temperature and thermal properties. VIRTIS-H, the high resolution channel, instead is a point spectrometer. It's not able to produce images, but gives a fine resolution on the coma gases. So it will allow to determine the gas distribution, the gas production rate, and so on.
And Fabrizio, I can just see that we have an image here, so probably it's easier for everyone if you switch to this side. What are we seeing here exactly?
Yes, this is an image which has been taken on the 29th of July, last week. And this covering is an animation that covers the full rotation of the nucleus, and the image in two spectral bands, the 1.4 micron, which is in the reflectance region, and the 5 micron, which is in the thermal emission region. And from the thermal emission, we were able to measure the temperature. Below there is a graph which shows the behavior of the temperature as the comet rotates. On top there is also the shape model rendering, that just to give the idea of how this object is taken during the rotation. And we were surprised to see this large temperature on the surface. So we see that there is a variation with the rotation, and we have a maximum temperature which is around 220 K.
So if I measure the temperature with a human being normally it's about finding out if he's well. When you say you're surprised about this temperature, does this tell you anything about the comet being well, not well, something unusual?
Well, it tells us already give us some information on the structure of the surface, of at least the first centimeters of the surface, which is saying, in fact, that from this maximum temperature, I repeat again, this is a maximum temperature, is not the average, tells us that the crust is porous, does not contain too much ice, but of course we see ice, we see water coming out, so there must be a way to come out for the water, but from these measurements, the maximum temperature is associated to a crust which is porous, dusty, and with no ice.
Okay. And temperature, of course, Fabrizio, thank you. And don't go away, because you will help Sam now as well. Sam Gulkis, who's standing next to me, and you're in charge of MIRO. And temperature measuring is also very big for you. Come a bit closer so we can see you in the light as well. MIRO stands for Microwave Instrument for the Rosetta Orbiter. But we're not talking about a microwave here. We're actually talking about a radio telescope. What exactly is it? Who's behind it?
Yes, may I move over next to the screen?
You can, of course.
Yes, so MIRO stands for Microwave Instrument for the Rosetta Orbiter, and it's basically a very small radio telescope, and we make up for size, for the small size, in being really close to the comet now. So we have very good resolution with the instrument. And just because it's small doesn't mean that it doesn't have really extreme capabilities.
And one of the real extreme capabilities, I think you took a measurement. You started in June, but you got a really, really good data in July. I think the next chart will show us something very interesting about the comet's coma.
Yes, I was going to just make one comment, and that is that this is the Ferrari of an instrument. This is not an Opel or a Fiat. It has a very high resolution capability, and one of the things that it does really well is it measures water around the comet. And the next slide that I will show you here will show what the water looks like to this instrument.
And there it is.
So here's a spectrum of water taken with the MIRO instrument. We first measured water in the comet in early June, and we have been tracking it ever since. There's a lot of information in this spectrum. If you look at it very closely, one of the things that you'll see is that the spectrum is not centered on zero. So the spacecraft is moving relative to the comet, and we have removed that Doppler shift from it and shifted it all back to where the water would be if we were looking at it in the laboratory. So if you look at it here, you'll notice that the spectrum is shifted.
I'll need you for the microphone. We have to keep it brief now.
Yes. So we're shifted over here into the negative side, and that means that we're seeing the gas from the comet rushing toward us. Mm-hmm. But the spectrum is also interested in what it doesn't show. You'll see that on this side of the spectrum, on the plus side, there's nothing. And that means that on the dark side of the comet, there is very little gas.
And all of this you found out in this very brief period of time, so there's lots more to come. Sam, Fabrizio, Holger, thank you very much. I'm afraid we have to leave it at this point, but talking about instruments on board of Rosetta, and of course waking up the orbiter, that took a long time, especially with all these instruments on board. You had to go step by step, but once it was awake, once it was up and running, these instruments could start to get down to work. So here's a look at some of the achievements Rosetta has performed since January.
Within 6 weeks of Rosetta's wake-up call, all of its 21 onboard instruments had been activated. The OSIRIS camera was the first remote sensing instrument to wake up for checking and operation. Without images from Rosetta, many scientists wouldn't be able to interpret the data from the comet, so it plays a key role in understanding the science. This was the first image of the comet from OSIRIS in 2011. Since then, it has been collecting more information, pixel by pixel, about the comet's rotation and shape, producing surprises along the way. Together with images from the navigation camera, This information will help mission controllers at the European Space Operations Centre in Germany to make orbital correction manoeuvres. Many instruments have been taking measurements since Rosetta was launched, including Rosetta, which measures material and gases coming off a comet.
We did already a lot of measurements during the last 10 years. We see all of the spacecraft dirt coming off. So our instruments work perfectly. They are extremely sensitive, and I look very much forward to finally see the comet and not only the spacecraft with our instruments.
The orbiter's miniaturized microwave instrument, MIRO, has also been in action. Built by an international team, it's the first instrument of its kind to have flown to the outer edges of our solar system. And during flybys of asteroids Steins and Lutetia, it took temperature measurements. From late May, MIRO turned its attention to the comet nucleus, measuring gases that are released as the comet approaches the Sun. In early June, MIRO made the first observations of water vapour streaming away from the comet, equivalent to 2 small glasses of water every second. But Rosetta's science has only just begun.
Now, in order to help Rosetta to continue with its scientific mission, a highly complex maneuver is necessary today. Frank Budnik is back with us again, flight dynamics expert. And you can tell us a bit more about this maneuver. Now, when we're talking about Rosetta going into orbit, it's not your usual orbit, is it?
Yeah, okay, it's not what we don't do today. We don't go into orbit around the comet today. And the reason for that is we don't know the comet or the physical properties of the comet sufficiently now. So what we want to do is we stay, let's say, close to the comet, and we fly next to the comet. If you see it from a solar system point of view, they're just flying next to each other, with Rosetta being closer to the Sun and the comet being behind, such that the Sun always illuminates more or less the full nucleus of the comet, so that we can see it with our navigation camera. This is what we want to do. And we stay 100 kilometers apart. And then we have a very small relative velocity, so we drift a little bit away. And when we drift away, after a while, so after 3 or 4 days, we do a very small maneuver, less than a meter per second, to go back a bit, going up again. And we fly, and both flying around the Sun simultaneously, 100 kilometer distance. And then after 4 days again, another maneuver. So this makes this kind of triangle, which we fly in front of the comet as seen from the Sun.
So it's a very timid rendezvous, let's say, with Rosetta sort of tiptoeing around the comet on one side. But you said right now we have to do this because we don't know enough about the comet. But why this triangle? Why has this orbit been chosen?
Yeah, okay, first of all, we want to characterize the comet, how it rotates, measure its mass, identify landmarks on it, and we have to see it fully illuminated. And with a 100 kilometer distance and with this orbit, we see, let's say, the full nucleus in the field of view of the navigation camera. This is one goal. And the other goal is we see it slightly with different phase angles, so different illumination angles from the Sun. And then we see areas with shadows and without shadows, and this we can characterize landmarks very well. And also, this motion which we have 100 kilometer distance is a bit bended. Yeah, it's not a linear motion, so the Rosetta is bended a bit, and this bending is what we are using. Let's say this bending comes from the gravity attraction from the center.
So there is gravity?
There is gravity. Of course, there is gravity, but we don't know what the mass is, so we don't know how big it is. And this we need to know before we go into an orbit, a controlled orbit around the comet. So we use this bending of the trajectory, we measure this to get hold on the mass of the comet. This is what we need to know initially now to go further down and to go into orbit finally around the comet.
Exactly, which will happen later this year. Well, Frank, thank you very much for your explanation. Now, we're talking about this comet, and of course, Rosetta has been spending 10 years to chase it. But believe it or not, 50 years ago, we didn't even know that this comet existed at all. It was in 1969 when 2 astronomers in Ukraine, going by the names Churyumov, Gerasimenko, spotted this comet, giving it this rather complicated name, at least for me, which is why it's also dubbed 67P. And this is what we know about the comet and why it is important to study it.
Like its name, Comet 67P, Churyumov-Gerasimenko, is in 2 parts. It's a so-called binary comet, and pixelated images from Rosetta's Sirius camera in July also showed that it is shaped like a duck. Around 3 by 5 kilometres in size, it rotates every 12 hours and 24 minutes. Comet 67P is known as a Jupiter family comet because Jupiter's gravity controls the comet's orbit around the Sun. Some of these icy space rocks are ejected by collisions or gravitational changes and become comets. One theory suggests that binary comets are formed when two comets collide, melded together when the solar system was formed. Studying Comet 67P will give insights into its origins and activity.
A comet it's not a static animal. It really develops with time. The nucleus sits there, but then the outgassing, the gas coming out of it, that just increases as we come closer to the sun when the comet is heated by the solar radiation. That's when the gas starts pouring out, and that gives the cloud you see around the comet. And in that cloud is what we will measure.
Water can be found as a vapour in the halo or coma around a comet nucleus and in its tail, and in ice form in the nucleus itself. Scientists want to study how water sublimates on the comet, going from a solid to a gas without the liquid phase. Its tail is a comet's distinctive feature, and a comet can have up to 3 of them, made from dust, ions or plasma.
It's the so-called fourth state of matter we use to solids, liquids and gases, while plasma is the fourth state of matter. And what we're trying to do is to study plasma in the environment of the comet.
Comet 67P's 2 parts and complex shape will offer unique challenges to the mission. But studying comets will shed light on the emergence of water and life on Earth, and also inform us about the formation of our solar system.
All right, some 20 minutes ago, the manoeuvres started and Sylvain Lodiot has been watching the screen. What's the status?
Well, we have the telemetry back, and I can confirm the maneuver has just started nominally. All looks good.
Brilliant. Congratulations to that, first of all. But you still keep watching the screens because for the next few minutes, there's still a lot of information that we're looking for. What exactly are we looking at here?
You can see here that the chamber temperatures of the spacecraft have started. They were at 20 degrees. You can see them peaking up. They'll go up to 110 degrees. So this is all nominal right now. And you can see rates on the spacecraft starting to build up. I mean, it's quite tough for the spacecraft to do these maneuvers, so all looks good.
All looks good. So basically, we don't need to worry right now. You keep an eye on this now, Sylvain. I would like to talk to your colleague, Andrea Accomazzo, who I know is a man with nerves of steel. But I'll get back to you again when you can tell us really today's mission is accomplished, which is still a few minutes from now, as far as I understand. Andrea, come to me. Andrea, of course, we remember you from the big January Rosetta Wake Up. Andrea Accomazzo, of course, is Rosetta's mission director. And when I said nerves of steel, it took a bit longer. It took a bit longer in January to have you smile and say, "Yep, everything is nominal."
Well, it was definitely a totally different event. We had abandoned the spacecraft for more than 2 years, and we had no contact at all. We were desperately waiting for that contact. Here is totally different emotions today.
When Sylvain is smiling, the commands, I believe, were given in the past days, the last command yesterday. Is there still a challenge right now at this moment?
Well, the spacecraft still has to do the maneuver. As Frank described before, we still have to map this object, so we have to perform this small maneuver to gently drift around it as we want, to map it properly. It's clear that the spacecraft has to work and is programmed to do this, so we are waiting for this result today.
Okay, so you've done your job for the time being. Now it's down to Rosetta. What if, and I'm not saying it will, but what if Rosetta does not perform the maneuver now? Try again or game over? What's the situation there?
No, it's definitely not game over. We have finished our approach phase to the comet. We are there. We are drifting with a very small relative velocity, so there's no chance that we are going to miss the comet. In case anything goes wrong, we will drift a bit. It will take a few days for us to eventually come back, but we can do it now. There's no doubt that we are there.
And once it worked, now the signal, the first one that we just got, where does it come from? How does that work?
Currently, we are receiving the signal from our New Norcia station, which is in Australia, so it's doing quite a long travel through the solar system, and also on the Earth, it has to travel a few thousand kilometers before it gets into ESOC here.
And what are the next steps? Because we're waiting now a few minutes before Sylvain can tell us, and we keep an eye on the screens with him in just a moment. But what exactly is happening in these minutes? What are we waiting for?
Well, the maneuver will take, roughly speaking, a bit less than 7 minutes to perform this change on velocity of speed of the spacecraft. Once we have get the signal, we know that we have inserted the spacecraft onto the trajectory we need to fly, and it will mark a milestone in the project. This is the end of 10 years interplanetary flight. It's like driving on a motorway high speed, and what we start doing today is like entering a chaotic town with a lot of traffic where the signs are confusing, and this is what we have to navigate now from.
Okay, then let's just get a taste of your and Sylvain's and everybody's work here in the main control room, which is part of just keeping an eye on the screens and see what happens, and then wait for Sylvain saying mission accomplished. Thank you very much, Andrea, for the moment. Sylvain, say the famous words, please.
We're at the comet! Yes!
Fantastic, congratulations. Andrea, just briefly for a moment, the two of you here right now. You just said you never got it that clearly that Rosetta must be under pressure performing for us. How do you explain such a clear signal? Is that just luck today?
Well, I don't know. We've never seen the temperature of the thruster going so clean and so smoothly as today. So it's a fantastic result. Couldn't have been better. Now let's check the detailed performance of the maneuver offline.
Okay, so Sylvain, you can't go back to sleep now. Now the work begins, correct?
Exactly. And yeah, Rosetta was looking at us, knew that we were looking at her, so this is why she did it for us.
Brilliant. Well, you deserve it. Congratulations. Congratulations to everyone here and people over there already hugging as well. But before I hand over to all those happy people, we have another little video for you, because obviously Rosetta has produced some surprises already, like the best or the clearest signal just now as well. And now that we're finally arrived at the comet, close to it at least, there'll be more surprises to come, I'm sure. So here's a look at some of the science that we can expect in the weeks and months to come.
Rosetta is a scientific mission to understand the origin and evolution of the solar system. The 21 onboard instruments include sensors, spectrometers and cameras. Powered by solar panels that span 32 meters tip to tip, Rosetta is the first mission to completely rely on its solar cells for power beyond the main asteroid belt. These solar arrays, together with the antenna, must always point towards the Sun and the Earth. Located on the side of the spacecraft that will permanently face the comet are the instruments, such as the atomic force microscope, MIDAS.
This is a very special type of microscope that is able to make very detailed three-dimensional images of objects that we collect. So our aim is to collect dust particles, and then we build very high-resolution three-dimensional images of these dust particles.
Studying dust grains helps provide a bigger picture, since many scientists believe these particles slowly coalesce to produce the building blocks of our solar system. The first dust particles are expected to be collected within weeks of arriving at the comet. The 11 orbiter instruments also include CONSERT. This is in two parts, one part on the orbiter, another on the lander, and together they will provide an insight into the comet's nucleus.
This will be done by transmitting the radio wave through the comet. This transmission will take place between orbiter and lander. And from the signal transmitted through the comet, we will determine the properties of the interior.
CONSERT will operate during the descent of the Philae lander to the comet's surface, examining its density and structure. The 10 lander instruments will measure everything from the comet's magnetic field to the mechanical properties of the soil. As the lander remains busy in one place, the orbiter will spend the next 18 months examining the comet from every angle, until this unique and groundbreaking mission ends in December 2015.
And the gentleman here next to me is certainly looking forward to all the data and the findings that Rosetta will deliver in those 18 months. Mark McCaughrean, he is the Senior Advisor to ESA's Science Directorate. And Mark, I remember we were standing here also in January, and I was told that you're the man who likes to ask the big questions. Now we're close to the comet. What kind of questions will those be?
First, it's what a wonderful moment, right? I mean, we're there, we've arrived. 10 years we've been in the car waiting to get to scientific Disneyland, and we haven't even got out of the car yet, and look at what's outside the window. So it's just astonishing. The really big questions here are, where do we come from? Where does this solar system we live in come from? How was it put together? How was it assembled? And then how did the planets get built up individually? And how did water get to this planet which we live on? And maybe even the questions about where the complex molecules, the organic molecules which build us up, so water and life. I mean, these are questions which motivate everybody. And I think, Rosetta is indeed the Rosetta Stone as a mission. It will unlock this treasure chest as a clue to all comets, many comets in our solar system. There are trillions out there. But this is a baseline. This is the one we can now study in such detail. We can rewrite history and begin to understand our own history. And I think that's, a great thing for us. Scientific Disneyland, the big roller coaster waits us in November. That's the scary ride to go on. But we have all the other fun rides all the way through till next year. So we have a really great mission ahead of us. The end of this year is going to be frantic. The whole of next year is going to be thrilling. So it's a wonderful moment.
It's a wonderful moment indeed. We now know what the comet looks like from the outside. Now we're about to explore what it has in store for us inside, and much, much more. Mark, thank you very much, because I see behind you some gentlemen who I'm sure are more than happy that this maneuver just now worked so well with such a clean signal, as we found out. Of course, ESA Director General Jean-Jacques Dordain, and with him Professor Álvaro Jiménez, ESA Director of Science and Robotic Exploration. First of all, gentlemen, give us your broadest smile.
Oh, it's very easy, because I have lived a lot of events here in this very room, but each one is even better than the previous one. I think that it's fantastic. I think that when you when you imagine the sum of expertise which is behind that, because it looks easy, but it looks easy because there is a fantastic sum of expertise. When you see the enthusiasm of each individual, and when you listen to the different English accent, including from the English ones, you can say that I can say that ESA is a fantastic place to be and to work for, and I would like to thank very much, obviously, the member states for their support, industry for their fantastic spacecraft, and my colleagues. There are 4 generations of drivers here behind me, and they are all great. Thank you very much.
Thank you very much. And Professor Jimenez, how important is today's mission accomplished for the whole mission and especially, of course, for the science part?
Yes, today is very important because we get there, of course, and we have been working a lot just to get to this moment and prepare to analyze, to get close to the comet and to be able to understand it. I had actually prepared, we had a 3D printing of what we thought the comet was like, 67p, and I was going to unveil that, and I don't know if we can show that.
We can try. I'll just run with you. And then
this
here we are.
is how we thought that the comet was 1 week ago. So it's a model of it. Now, with the images we are seeing today, it's impressive, it's fascinating. It doesn't look like. So it is the core of exploration, because we are going to places we have never been. And all what we can model is nothing compared to reality. Reality is much more fascinating. And we are getting, of course, we go there to get answers to some of our questions in science, like questions about the origin of the solar system, the origin of water on Earth, the origin of complex molecules on Earth. But what we are really interested in, not only in the answers, we are really, as scientists, interested in the questions. We are getting many more questions than answers, and the new questions are fascinating and opening a new world of exploration and science for the coming decades.
Absolutely, and as you just show us this beautiful model, now that we have those gorgeous pictures from Osiris, and there'll be even better ones coming later today and in the coming days, soon you'll be doing a new model. It's a bit like unwrapping a Christmas present with each layer, isn't it?
It's like a picture being developed. I mean, it goes with the time, it gets more resolution, it gets better, and we learn a lot. For example, today we know now about the temperature and what is the effect. I mean, it's not like comets used to be called as just ice rocks or dirty rocks. Now, this may be more dirty than ice, actually, with more, and this we didn't know. Now we see a lot of things that we will have to see what is the implication of this and how this is this comet came into this configuration.
Well, Professor Jimenez, Jean-Jacques Dordain, we look very much forward to all the new findings, the new models, the new science that will come. Thank you very much.
Thank you. This is Christmas every day.
This is Christmas every day. Beautiful last words. Thank you very much. And well, this wraps up our special coverage of this Rosetta meets the comet rendezvous. Today's mission has been accomplished, but of course there are many more to come, so do keep an eye on this spot. For now, from me and the whole team here at ESOC, it's bye-bye and hopefully see you soon.
Downstairs in the press center at 1 o'clock. So please, we see each other back at 1 down in the press center. Thank you very much.